Hey guys, if you are watching this video, I'm assuming you've been doing a lot of factoring. Now, in this problem, we are looking at a very specific type of factoring, which is the sum or difference of two cubes. This is when you have a problem that maybe looks a little tricky to factor, and you notice that all of them are perfect cubes. Now, if you need a quick review about what perfect cubes are, I got you. So you're probably pretty familiar with square roots, like the square root of 16 is 4. And why is that? Because when I do a square root, it's asking me what number multiplied by itself will give me 16. So because 4 times 4 is 16, the square root of 16 is 4, right? Now, cubed root is really the same thing. We are just asking, you probably guessed it, what number multiplied by itself 3 times will give me the number that's over here. We put a little 3 to signify that. So for example, the square root of 125 would be 5. And that's because 5 times 5 times 5 times itself 3 times is 125. So as you can probably imagine, there are a lot of numbers that do not have a pretty cubed root. You're going to get an ugly, nasty decimal. So a perfect cube is when we get a nice integer for our answer, like 5 or 10 or 4, right? So that is what a perfect cube is. So when I know I'm going to be working with problems like this, I tend to like to write them out so that I just have these ones right here that I know are perfect cubes. Now, as you work with problems like this more, you will start to recognize these numbers just right off, but I like to have them written out just to help me. All right, now let's go ahead and look at a problem. All right, so let's see how this applies to this problem. Here is our sum or difference of two cubes. So obviously in this one, we are subtracting, so we're looking at the difference. What I need to do is to get each of these terms to be to the third power. So for example, if I look at my list here, which obviously I could have gone on literally forever, but I stopped at 7 cubed. If I look at this, I notice, oh, 216 is 6 cubed. So I could rewrite 216 as 6 cubed. Okay, I am one step closer. I got one of my terms written as a cubed. Now can I get the other term? Well, 125 is 5 cubed. So I can write 125 as 5 cubed. Then we just got our variables here that are to the power of 15 and 9. And it's pretty easy to get these to be to the third. If you need a quick exponent review, I'll link one in the corner, but I'm going to go over it a little here too as well. So whenever I have exponents, if I have an exponent raised to another exponent, so for example, if I have f to the 5th cubed, that would be f times itself 5 times 3 times, right? So all you do is multiply your exponents. So this would be 5 times 3. So it would end up being 5 to the 15th. So what I can do here is instead of writing f to the 15th, I can write it as f to the 5th to the 3rd. All right, those are the same thing. They would both simplify to f to the 15th. Now, what about g to the 9th? Well, if I have g to the 3rd to the 3rd, I multiply those and get g to the 9th. So I can write g to the 9th as g to the 3rd to the 3rd. All right, that looks a little scary. So I want to get rid of some of those parentheses, and I can just write it as 6 cubed minus, now since each of these are to the 3rd, sorry, my writing got bigger, that's weird. But since they're each to the 3rd, I can actually write this as 5 f to the 5th, g to the 3rd, and all of those are to the 3rd. So you could even double check and make sure that if you multiplied that out 3 times, you got this. All right. Well, now I have a term cubed and a term cubed. So now I just need to figure out what my x's and y's are and plug them in here. So my x is whatever number is in the front, right? So it's 6 here. This is my x. I can write it over here as well. In this case, x is 6, right? And my second term is this 5f to the 5th, g to the 3rd. That is my y. So I can write that over here as well. X is 6. Y is 5f to the 5th, g to the 3rd. So now I am just going to plug in x and y for all of these x's and y's. So first I have x minus y. Again, this is minus, so we're doing the difference. The only difference between them is those signs, but we need to make sure we do it correctly. So when I plug these in, I have x minus y. So I'm going to write it as 6 minus 5f to the 5th, g to the 3rd. Okay, that's already that spot. Then I have x squared. Well, x is 6, so 6 squared is 36. There we go. Plus x times y. So I'm multiplying these two together. So 6 times 5 gives me 30, and we are adding this. So plus, when I multiply these together, I get 30 f to the 5th, g to the 3rd. And then I just add y squared. All right, so remember, this is my y. If I'm squaring that, we can write it out if we'd like to. So f to the 5th, g to the 3rd. We are squaring this. Well, the square needs to go to each one, right? So 5 squared would give me 25. F to the 5th squared, remember I multiply those, so I would get f to the 10th. G to the 3rd squared, I multiply, so I would get g to the 6th. So that is the term I am plugging in right there. That is y squared. So plus 25 f to the 10th, g to the 6th. And guess what? I know it's probably not the most beautiful thing you've ever seen, but that is my answer. Now you're probably like, we like our answers to look more simplified than when we started, right? But we're factoring. So if you were to multiply this all out, you would end up with this. And you can always do that to double check and make sure you factored correctly. All right, if you need some more sum or difference of two cubes videos, I will link a playlist in the corner. Thanks.